Okay, this is the first lesson video for AP Calculus AB, and what I'm going to cover in this video are sections 2.1 and 2.2. What we're going to look at here are really just the basics of limits, what a limit is, and then also how do we go about solving some limits. Normally in this class, we don't cover two sections in one day. However, we're looking at material that, number one, is closely related, and number two, is fairly easy. So what we're going to do is go through a lot of these basics, and a lot of this, as you go through the video, is going to be you working through examples to make sure that you've got a good understanding of how limits work. So in this chapter, it's really chapter 2 is our first unit where we're going to start talking about calculus. And the big thing to remember is that everything that you do in calculus is based on the idea of a limit. So even though once you wrap your head around this, this is very simple, keep in mind that this is stuff that you are going to be using not just in AP Calculus AB, but if you take BC next year, or you take Calculus 2 at college, if you take a Calculus 3 or a multivariable calculus class, you're still going to be thinking about limits. So it's very, very important not just to be able to get the answer to a limit question, but to understand what does it actually mean when somebody asks you to find a limit. So the first thing we have here is the definition of a limit. And this is the mathematical definition of a limit. So it's a little bit confusing because it's written in mathematical language, but at the same time, this is the way that we actually describe mathematically what it means for a limit to exist. So if you notice here, it says f has limit L as x approaches c if given a positive number epsilon, there is a positive number delta such that for all x, these two conditions have to be met. Okay, so when we talk about these conditions, I'm going to show you on the graph what this is really referring to. This is saying the distance between x and c is somewhere between 0 and delta. And notice that when we're talking about c, we're talking about what's happening along the x-axis here. So essentially what we're doing is we're moving closer and closer to the value of c from both the right-hand side and the left-hand side. So whenever you see an absolute value, remember that's a distance. So as I approach from the right-hand side and from the left-hand side, if that's happening, then if the limit's going to exist, then the distance between my function value and the limit value should be less than epsilon, where epsilon is going to be some small value. And essentially what they're describing here is we're moving along this function towards the same point from both sides. So the big thing to remember is the actual value of the function at that point is not important. What we're trying to do is we're trying to figure out what's the trend of this function. You know, what's the behavior of it? It's trending towards a value of L from both sides. So again, you notice on this graph, it looks like there's a hole in the graph. That has no bearing on what the actual limit value is going to be. Okay, so if those two conditions are met, then that means the limit as x approaches c is equal to L. And there's a much easier way for us to write this. And you can see there's this informal definition of a limit down here. If f of x gets closer and closer to a number L as x approaches c, then the limit of f of x as x approaches c is L. And so essentially what we're saying there is as we approach the x value from both the right and from the left, if our function is approaching the same function value from both sides, then our limit is going to exist. Okay, so for a limit, it's always got to be a single number, and that is essentially what I'm saying when I say the right-hand limit and left-hand limit have to be equal to the same value. That value that both one-sided limits are equal to, that's what the overall limit at that point would be equal to. So what we have down here are three different looking graphs, but the point of these three graphs is to show you that even though we've got different behavior at the point where x is 1, the limit as x approaches 1 is actually the same on every one of these graphs. So if you look at this first graph, you can see that we've got a hole in our graph there at x is 1. However, if we were going to evaluate the limit as x approaches 1, you can see as we approach from the left and as we approach from the right, both of those are going to approach the function value of 2. So my limit there is going to be equal to 2. Same thing on this second graph. The second graph looks a little bit different because we've got this point here that's sort of removed from where the rest of that line is. However, from a limit perspective, everything's still the same. I don't really care what's happening at that point. What I care about is from the right and from the left, I'm approaching the same value of 2. And then on the third one, same idea again. This time we've got a point actually filled in. This is what we call a continuous function, but you can see we're still approaching the same point. So the actual value at the point doesn't matter. What matters is what's the trend of the function? What are we trending towards from both sides? Okay, here is some notation that we use to represent what we call one-sided limits. One-sided limits are what I was doing essentially with drawing those arrows on the graph. So when I say x approaches c and then we have this plus, like you see here, that's indicating we're approaching from the right-hand side. So that's my right side limit. And then when I see x approaching c with a minus, that means we're looking at the limit approaching from the left. So as sort of a shorthand way of writing the definition of a limit, notice what this theorem says. It says the limit as x approaches c of f of x is equal to L, and that's if and only if these two conditions are met. The limit from the right of that function is L, and the limit from the left of that function is also L. This is typically what we use when we justify a limit existing. What we typically use is the idea that we show that the right-hand limit and the left-hand limit are equal to the same value. Therefore, the limit at that point is equal to the same value. So keep that in mind. All right, so let's take a look at a limit graphically. So that was the idea of a limit, just kind of talking about it in general. So what we're going to focus on a lot here is now actually evaluating some limits, primarily graphically as we go through this section. But we'll get into a little bit of starting to evaluate them as well as we move further along. Okay, so we've got a function here, absolute value of x over x. This is a graph that you guys are going to see a lot in this class. And when you graph it, you could graph that on the calculator if you want. But this is a graph you should be able to create very quickly without a calculator or just know what it looks like. So what I've got here is a y value of 1 and a y value of -1. As I move to the right on this graph, anything that's a positive value is always going to give me a value of 1. So for example, if x is 1, I have absolute value of 1 over 1, or x is 2, I have absolute value of 2 over 2, and so on. So I'm essentially dividing the number by itself. The only difference here is when I look at negative values. When I look at negative values, my graph is always going to give me a value of -1, because think about if I plug in -1, for example. The absolute value of -1 is 1. That would be divided by -1. That's going to give me -1. Okay, so notice I put these holes in my graph here. So these holes are there because there's no value defined at x is equal to 0. Okay, so now once I see that, if I look at my right side limit and my left side limit, the limit as I approach x equals 0 from the right would be 1, and the limit as I approach 0 from the left would be -1. So since those two are not equal, for this limit, I would say this limit does not exist. For does not exist, we're typically going to write DNE, indicating the limit does not exist. And that's always going to be when the left-hand limit and the right-hand limit are not equal. Okay, so what we have down here is an example that I want you to try. It is a graph that's been created. It's a piecewise graph. And they ask you for a bunch of information about limit values and function values. So what I want you to do is pause the video and try to answer these 8 questions. And when you've got them all done, unpause the video and I'll go through the solutions. Okay, so here's what you should have ended up with. And I'm going to delete these boxes for you so you can see the solutions. And what you can see here for the limit as x approaches 2 from the left, all I'm doing is I'm referencing this graph, right? So right now I'm looking at the limit as x approaches 2 from the left. I look like I'm approaching a value of 1. From the right, I'm approaching a value of 1. Notice that this point at x equals 2 doesn't have an impact on my overall limit value. these two limits that I've starred here are both equal to the same value. The one-sided limits are the same. Therefore, the limit as x is equal to 2 is also going to be equal to the same value of 1. All right, and notice the function value that we have here and the limit value don't match up. That doesn't have any impact on whether or not the limit exists. That would have an impact on something we call continuity, which we'll talk about next time. But for today, in terms of just purely looking at it from a limit perspective, that function value is irrelevant. Okay, so now let's look at the same thing as we're approaching 1. So we're approaching 1 from the left and 1 from the right. And so we're kind of looking at this portion of the graph. From the left, we're approaching 0. From the right, we're approaching 1. And you can see that those two are not equal, so the limit wouldn't exist. And again, notice the function value. This is a function value at 3. That's completely different than what we're talking about here. But let's say we were talking about the function value at 1. Well, the function value at 1 would be 1, but the limit still doesn't exist. When we talk about this point over here at 3, you can see that at that point, that's what we call continuous. My left-hand limit and my right-hand limit would be the same, and the function value is the same as well. They're all equal to 2. So when it's continuous, those are all the same. But for us, when we're just talking about limits, remember, you're just looking at the left-hand limit and the right-hand limit. Okay, so let's move on, and we'll talk a little bit about finding limits algebraically. So they're going to have some basic limits that you're going to solve in this section as well. And algebraically, we have some different options that we can use to solve. Now, we saw some graphs where we had things like removable discontinuities in the graph or jump discontinuities in the graph as well. And when we see things like that, we're going to use algebra to solve these limits out. Our most basic method for solving a limit is what we call direct substitution. So let's look at this first problem. It says the limit as x approaches 3 of x squared minus 2x. Well, direct substitution just means I'm going to plug in this value of 3 into my function. And if I get a value, that means the function's continuous there, so the limit's going to be equal to that value. So in this case, this would just be equal to the limit as x approaches 3, and that would be, I could write it as, if I want to, 2x squared minus x cubed. But in the end, that's going to be the same as plugging 3 into this. 2 times 9 minus 27. And that's going to give me a value of negative 9. Okay, so pretty simple to do when it's continuous. Now, look at the next one. We've got a rational function. You're going to see several of these that are rational functions. When you have rational functions, it's kind of the same situation. If we had a removable discontinuity, you want to think back to your prerequisite knowledge. If something is removable, then what I'm going to want to do is I'm going to want to divide out that removable discontinuity. So for example, in this case, if it was removable, I would be able to divide out the x plus 2, and then I'd be able to evaluate the limit. But we're not going to be able to do that in this case. So instead, what we have here, if you look at the numerator, we're evaluating at 2. I'm going to get a non-zero value in the numerator, but more importantly, in the denominator, I'm also going to get a non-zero value. So by direct substitution, essentially what this is 4 plus 4 plus 4 in the numerator, and in the denominator, I have 4 as well. So that's going to give me a value of 3. So again, that was a continuous function. It was very easy to solve. If we had had some sort of removable discontinuity, we would do some algebra and simplify that out. All right, and here is one more where we've got sort of a special case. We have the limit as x approaches 0 of the square root of x squared plus 9 minus 3 over x squared. So I mentioned that we can do some algebraic manipulation when we have issues with these. So the first thing we typically try is factoring. Well, on this problem, we've got a square root. If I were to plug 0 into the numerator, I would get the square root of 9, which is 3, minus 3, that's 0. But in the denominator, I also have 0. So essentially, this looks like 0 over 0. When I see a 0 over 0, that's usually indicating to me that there is some sort of a special feature on my graph. Typically, it's going to be a removable discontinuity. So since I didn't get an actual value when I solved that out, what I'm going to do here is I'm instead going to try something a little different. I can't factor this, but when we have these rational expressions with roots in them, sometimes we can multiply by the conjugate. So the conjugate is just the same expression that we have in the numerator in this case, because I'm multiplying by the conjugate of the square root expression. I'm going to multiply that to both the numerator and the denominator. And let's see, that was plus 3. So when I do that, notice that essentially what I'm multiplying by is 1. I'm not actually changing the value of the function, I'm just changing the form that it's in. And by doing this, what I'm hoping is going to happen is that the discontinuity that I had at 0 is going to somehow cancel out, and I'm going to be left with a function where I can evaluate the limit. So when you multiply this all out in the numerator, you're going to get x squared plus 9 minus 9. In the denominator, you've got x squared times the square root of x squared plus 9 plus 3. So notice what happens here. These 9s are going to cancel out. Once that happens, and this should be a square down in the denominator. Once that happens, now I've got x squared over x squared times the square root of x squared plus 9 plus 3. So now I can cancel out these x squareds, and what I'm left with is the limit as x approaches 0 of 1 over the square root of x squared plus 9 plus 3. So you may remember this from pre-cal when you would remove the discontinuity from your function so that you could figure out where the hole in the graph was. That's essentially what we've just done. And now when I solve this out and I plug 0 in, I'm going to end up with 1 over the square root of 9 plus 3, or 1 over 6. So if you were to graph that, and you can do this on your own if you want, if you were to graph that on your calculator, you would see there's actually a hole in the graph at x is equal to 0, but you can see from both sides, from both the right and the left, on your calculator, you can see that the function is approaching a value of 1/6. So the right side limit and the left side limit would be the same in that case, so the limit's equal to 1/6. Okay, so let's move on to the next section. So in that first section, you're going to have a lot of problems where you're just going to be solving limits. Some of them off of a graph, some of them algebraically, like we just did there. There might be factoring involved. You might be multiplying by a conjugate. There's different things that can show up, but it's all fairly straightforward, and you just need to practice a little bit with it. If you're good with your prerequisite skills, then it should be pretty easy to do. All right, in the next section, we have what we call limits that involve infinity. And when we talk about limits involving infinity, we're talking about limits where the actual limit is approaching an infinitely large value, or a value that approaches negative infinity. Or we can also be talking about behavior around a vertical asymptote. So remember back from pre-cal and algebra 2, when you have a vertical asymptote, you have a function either increasing to infinity or decreasing to negative infinity around a vertical asymptote. Okay, so let's start with talking about vertical asymptotes. So when we say our function is approaching infinity, like we see here, that would be a situation where on both sides of that asymptote, my function would be getting infinitely large. And this notation's a little bit confusing. So technically, nothing can be equal to infinity. But when we can, we want to describe the behavior of the function as accurately as we can. So if I've got the same behavior on both sides of a vertical asymptote, I'm going to say that the limit approaches infinity or negative infinity if they match up that way. I will use does not exist in situations where I've got those two things not matching up. I've got different behavior on one side of a vertical asymptote than another. But technically, even when I write it in this form that I've got circled here, that limit still technically fails to exist because we can't be equal to infinity. So if you were to see this as a multiple choice question, I would expect that most of the time on a multiple choice question, you would say the limit would be infinity. but it also could show up and it could have an answer choice that says, does not exist. And that would technically be correct. So you would see one or the other if it were a multiple choice. The correct answer saying infinity or the correct answer saying does not exist. So keep in mind, we write equal infinity not because it's actually equal to that value, because infinity is not a value. We write it because it's allowing us to describe the behavior of the function. Okay, so when we have a vertical asymptote, on either side of that vertical asymptote, I'm always going to approach infinity or negative infinity. And that's what we're going to look at here on these next couple of graphs. And we're also going to talk a little bit about horizontal asymptotes as we go through this. Okay, so we've got several problems here that we're just going to talk about. And the first one says we're looking at this f of x graph. And notice here, it says f of x. It's kind of small. It's hard to see. And over here, it says h of x. So when these limits refer to f of x and h of x, that's what they're referring to. So what I'd like for you to do is just take a minute, pause the video, and see if you can solve out all of these limits and function values that they ask you for. Okay, so now that you've attempted those, let's talk about what you should be getting for those values. So the limit as x approaches 2 from both the left and from the right looks like it's 3. So for this one, we'd get 3. The limit as x approaches 0, notice that from the left and from the right, we're seeing different behavior. So this one would be a does not exist. The limit as we approach 0 from the left looks like it would be -2. 0 from the right would be 0. And remember, what I'm looking at here is I'm just looking at these two branches of my graph to figure out what those limits are. And then it says, what is f of 2? Well, f of 2, notice that value looks like it's actually equal to 1. And remember over here, we said the limit as x approaches 2 was 3. And it displayed as gray, but that's supposed to be a hole in the graph there at 2. You notice that point is removed from where the rest of that graph is trending. So even though we've got a function value that's different than the limit value, it doesn't impact the limit value. All right, and then number 6, it says, what's the limit as x approaches -infinity? So this is our limit notation when we're talking about horizontal asymptotes. And you guys saw horizontal asymptotes in Algebra 2, but you usually don't talk about them in terms of limits. And you probably saw them in pre-cal as well. So as we're approaching -infinity, what we're looking at is, what is this portion of the graph approaching as we move in that direction? And you can see it looks like they've even got it graphed in here. It looks like we're approaching a value of -1. So when you see a limit like number 6, that's describing a horizontal asymptote. All right, so on number 7, it says, what's the limit as x approaches infinity for f of x? It's kind of hard to tell. I would say it looks like this is probably approaching 0. I don't really 100% know for sure that that's the case, but it does look like there's a horizontal asymptote that I'm starting to flatten out as I approach. So I'm going to assume that that one's 0. All right, so 8 through 11, we're going to look at the other graph. So number 8, it says, as we approach 1 from the right, and 1 from the right, it looks like we're approaching -infinity. Notice how this is really pointing down in that direction. We're getting infinitely small in terms of the number, but the magnitude is getting very large, but it's negative, so we're approaching -infinity. Okay, so these two problems at the bottom of this page, it says use a calculator to find. And for the first one, this is one where you may actually need a calculator. If you really wanted to, you could probably sketch this graph just using your prerequisite knowledge, understanding how to deal with vertical asymptotes, and maybe testing a few points. But if you graph this on the calculator, what you're going to see is that you've got different behavior on the two sides of this vertical asymptote at x is equal to 2. On one side, we're going to infinity. On the other side, we're going to -infinity, or we're trending towards -infinity. So that means this one we would write as does not exist. So pretty simple. The second one, even though it says to use a calculator, you can graph this on the calculator if you want, but really this is a matter of reasoning. And typically with the limits as x approaches infinity, we're just going to reason through them. When x gets very, very large, we've got sine x over x. In the numerator, that value is going to be bounded between -1 and 1. Sine never gets smaller than -1. It never gets bigger than 1. But in the denominator, that's going to get infinitely large. So even though I might go back and forth between positive and negative numbers, since the magnitude of the denominator is so much larger than the magnitude of the numerator, eventually this is just going to approach a value of 0. And if you think about a really large number plugged in, like a million, sine of a million, I don't know what it is. I know it's between -1 and 1, and it's very small compared to dividing by 1 million. So that's going to obviously approach a value very close to 0. Okay, so the next problem that I have for you here is involving what we call the squeeze theorem. I think your book may refer to it as the sandwich theorem. It means the same thing. But what this is it's another method for us to solve limits. So what we've looked at so far is we've looked at limits graphically. We looked at them algebraically a little bit. We can look at them numerically where we just plug points into the function and kind of see where it's trending. But the last method, when those fail, is what we call the squeeze theorem. And the squeeze theorem is a way for me to work with a function without actually directly doing any calculations with that function. So what we're looking at here is the graph of g, f, and h. And the function that I'm interested in evaluating is this function f. And notice that it falls between g and h. That's what we call a bounded function. So we have bounded f between g and h. G is the upper boundary. We know f's never going to go above g. H is the lower boundary. We know that f is never going to go below h. So we have an upper bound and we have a lower bound. So that means our function is bounded. Okay, so what we've got here is an example of how this works. It says if h of x is less than or equal to f of x is less than or equal to g of x in some interval, and if, this is the key part, if these two things are true, our limits of the outside functions are equal. So notice they're not doing anything with the f function. They're dealing with the h function and the g function. If the limits of the upper bound and the lower bound are equal, in order for this original statement here to be true, f of x is going to have to be, or it's going to have the same limit at that point. And that's what our squeeze theorem says. Okay, so here's an example of that. We've got x squared sine 1 over x. It says find the limit as x approaches 0. Well, the problem with this, evaluating this, if you try to do direct substitution, you get sine of 1 over 0 or sine of an infinite value, right? Or an undefined value. So there's no way for me to evaluate this just by substitution. And our only other fallback option, if we didn't have this method, would be just graph it on the calculator and look at it. And that's one of the things that this is mentioning to do. You can graph this on the calculator. However, there's an easier way to go about this. So what we're going to do here when we use the squeeze theorem is we're going to start with a statement that we know to be true. So we had that whole thing about the f and the g and the h functions. Well, we're usually not going to call them that. We're just going to start with a statement we know is true. So remember, the limit that we're trying to find involves an x squared times the sine of 1 over x. Well, I don't know anything about that function. But what I do know is any sine function can't be bigger than 1 and it can't be smaller than -1. So with that being the case, this step that I've circled here, that's sort of my starting point. And once I've got that, now I'm going to manipulate that expression so that the function in the middle becomes the function that I'm trying to find the limit of. So I can multiply everything in this inequality by x squared. And now I've got a statement, this next statement, where I have now bounded the function that I'm trying to find the limit of. So x squared sine 1 over x is bounded between x squared and negative x squared. So take the limit of the two outside parts. Notice they're both the same. Since those are both the same, that means the limit of the function in the middle at that point is also going to be equal to the same value. Okay, so this is kind of a specialty type of limit application, but this is something that has a lot of long-term uses within calculus. This whole idea of comparing functions is something that we use a lot when we get into, if you take Calculus 2 or BC Calculus next year, we get into a lot of stuff with infinite series, where we can't actually deal with the function or the series that we're looking at. So we find things to compare it to that are similar. And based on what's happening to the similar functions, we can conclude what's happening about the function we're looking at. So you'll see it a little bit in this course where we use squeeze theorem, but really long term, you won't see this a lot until you take Calculus 2 or BC Calculus next year. Okay, so there is a special case of the squeeze theorem. And we have this limit that's in the box here. And this limit is one that for now, I just want you to memorize it. There is a proof for this limit involving the squeeze theorem. It's kind of complicated. I'm not going to go through it in this lesson, but on the last page of these notes, there is a detailed explanation of how it works. I'm not going to go through it in a lot of detail. In fact, I'm not going to go through it at all because it's all written out there and it's something you don't have to know. But if you're somebody who is going to continue on in calculus, if you're somebody who thinks you might have an interest in mathematics long term, this is something that would be really important to you. So on the very last page, there is the proof for why that is true. The limit as x approaches 0 of sine x over x is equal to 1. Okay, so for now, what we're going to do is just sort of memorize that that's true. There is a way that we can show that that's true using something called L'Hopital's rule, but we won't do that until the end of the first semester. So this is a limit that we see a lot, and I don't tell you to memorize a lot of things in this class. That's something that you're going to need to memorize. So that is an application of the squeeze theorem, but we're not going to go through all the steps. Okay, so here's one example where what I want you to do is just go through and I want you to find the limit as x approaches 1 of this function based on the fact that we have the function bounded. So you can see we already have our statement that bounds our function between 1 and x squared plus 2x plus 2. And what I want you to do is try to think about the squeeze theorem and think about what would that limit be equal to. Okay, so let's go through and talk about how we would actually solve this out. So remember before I started with that sign of 1 over x and I bounded it between -1 and 1. Well, they've already come up with the bounded statement for us. So all I'm going to do here, I know I'm interested in the limit as x approaches -1. So the limit as x approaches -1 of 1, which is my lower bound, that's equal to 1 because that's the function y equals 1. It's always going to be 1. If I took the limit as x approaches -1 of x squared plus 2x plus 2, well, think about -1 plugged into that. I'm going to get 1 minus 2 plus 2. That's going to give me 1. Well, those two limits were the same. Those were the limits of my boundary functions. So since that's true, I can say therefore, that's how we write therefore in shorthand for math. Therefore, the limit as x approaches -1 of f of x is going to be equal to 1. Okay, so pretty simple to do. That's the type of squeeze theorem that I might ask you to apply, something simple like that where it's a very, very simple function. Maybe you have to write the bounds or maybe it's just given. But the main thing is to understand with the squeeze theorem, if the outside limits are the same, then the limit of the middle function has to be the same at that point. Okay, so now what I've got for you are just some practice problems to make sure that you've got this down before you jump into the homework. So there are, I don't know, 12 or so limits that I want you to try to solve on this page and the next page. So I want you to pause the video, take a few minutes and try to solve through these limits. And then when you've got them all answered, unpause the video and I'll go through the solutions for you. Okay, so for this first one, the limit as x approaches 7 of 5, you're going to get 5. That's just like looking at the line y equals 5. It's always going to have a value of 5. The limit as x approaches 3 of x, for that one you should have gotten 3. That's just the line y equals x that you're looking at. It's a continuous function. The x value is the same as the y value, pretty straightforward. This next one's a little trickier. You should have gotten a value of 5. You probably didn't know how to solve this one. And what you can do in a situation like this is graph it, and you would see that the function value is approaching 5. It's actually undefined at 0 because you get 0 over 0. We've got a hole in the graph, but it's approaching a value of 5 from both the left and from the right. The other thing is, this is another one of those, it's that special case of limit as x approaches 0 of sine x over x is 1. This is a special case of that. So it's one of those rules that for now you're going to want to remember. And then eventually when we get to L'Hopital's rule, you'll have another method to solve this. So as a general rule, whatever you multiply the argument by in the sign, in this case it's that 5, that's going to multiply the limit by the same value. So if this had said sine 10x over x, it would have been 10. If it said sine pi x over x, it would have been pi, and so on. So try to keep that in mind as just a special rule. All right, so let's move on here. The next one, the 1 over x minus 2 squared. There'd be a vertical asymptote there, and you have the same behavior on both sides. It's approaching infinity. That's a graph you should be able to do based on your prerequisite skills. You should be able to identify that's a vertical asymptote. You should be able to figure out what the shape of the graph is around that asymptote. The next one here, we've got 5x plus sine x over x. And I'll show you the solution. Where this comes from, when you solve these infinite limits, there's usually not a lot of work involved. It's more a reasoning process. So what I'm looking at when I solve this is I look at the numerator. And I'm going to evaluate the numerator and the denominator kind of separately for a second. So 5x plus the sine of x. When x gets very, very large, think about the sine function being bounded between -1 and 1. Sine's never going to get bigger than 1 or smaller than -1. If I'm looking at a really, really large value of x, like let's say x is 1 million, I'd have 5 million either plus or minus, as much as 1. Well, that 1 is becoming almost insignificant. So what that tells me is, as x gets very large, what's important is going to be the 5x and the x. So from that, I'm essentially saying when x gets really big, this graph is essentially going to look like 5x over x, which that's just going to give me a value of 5. All right, next problem. We have another one where we need to multiply by the conjugate. So I showed you one like this earlier. You should have multiplied by the conjugate, and that would give you a value of 1/6. If you multiply by the conjugate correctly there, the x minus 7 should cancel out. The limit as x approaches 0 of 1 over x. You should have gotten that does not exist. That's a graph you should just know. And if you don't, that's one that you need to practice with because you're going to see 1 over x all the time. Sine x over x, the limit as x approaches 0 is 1. We talked about that earlier. That's the one you should have memorized. So the next one here, we've got x squared minus 9x plus 20 over x minus 4. That's one you need to solve by factoring. So if you plugged 4 into the original expression, you would get 0 over 0. If you go through and factor and cancel out the x minus 4, we're left with x minus 5, which then when you plug 4 in is -1. Essentially what I do when I cancel out the x minus 4 is I eliminate that removable discontinuity and I turn it into an equivalent continuous function. And now I can see that the function is trending towards -1. Tangent x over x. So we had the rule for sine x over x, and we're just going to manipulate that rule to come up with this solution. So sine x over x is the limit value that we know to be 1. So what I've done is I've rewritten the tangent as sine x over cosine x. And now just doing rational expression manipulation, I'm multiplying the 1 over x into the numerator because we were dividing by x. So I'm multiplying by 1 over x, and then I just grouped it together. Sine x over x times 1 over cosine x. And by grouping those two things together, now look at these limits independently. If I look at sine x over x, the limit as x approaches 0 is 1. If I look at 1 over cosine x, well, as x approaches 0, cosine's approaching 1. So I essentially have 1 times 1, which is 1. These next two limits are just really reasoning through numerically what's happening. as x gets very, very large, notice we have e to the negative x. So if x was a really big number, like let's say 1,000, I would have e to the negative 1,000th power, which is the same as 1 over e to the 1,000th power. Well, 1 over e to the 1,000th power is just going to approach a value of 0, right? It's getting very small. So essentially what's happening here is I'm looking at x over x when x gets big, and that's going to approach a value of 1. In a similar way, on the next one, we're approaching negative infinity with this limit. So think about a large negative number plugged in. So when I say large, I mean large in magnitude, like negative 1,000. Well, if I'm plugging in a negative and I have this negative as part of my exponent, if I plug in negative 1,000, that becomes e to the 1,000th power. E to the 1,000th power is much, much larger than negative 1,000. So in the end, what becomes insignificant on this one is this part, and I'm essentially just looking at those two expressions as sort of dominating the value of the function when x trends towards negative infinity, and that gives me a value of 1. The next one here is another one where you're just going to multiply by the conjugate. You should see the h cancel out. You're going to get 1/2. This one's a little tricky. We have the sine x over x form, but notice it says x is approaching infinity. Remember, the numerator is bounded between negative 1 and 1. The denominator is getting infinitely large. So that's going to approach a value of 0. And then this last one is just kind of a special case that I wanted to show you. We have the limit as x approaches infinity of the sine of 1 over x. So what you can do in situations like this is you can rewrite these limits, and you can rewrite them in a form so that essentially, instead of taking the limit to infinity, you can make it 0. Instead of 0, you can make it infinity. And it all has to do with the graph of 1 over x. If you think about the 1 over x graph as x approaches infinity, that graph approaches 0. As x approaches 0 from the right, you're approaching infinity. And so I'm going to manipulate this 1 over x. That's why I'm talking about the 1 over x graph. So I'm going to rewrite this as the limit as x approaches 0, and I'm going to take the reciprocal of all of the x expressions. So that's equivalent to saying the limit as x approaches 0 of sine x. Notice that this changed from an infinity to a 0. So this rule is used in rare circumstances when you're trying to deal with something that has a 1 over x in it, and you're trying to find another way to work around it. This is not one you're going to have to use a lot, but it's a special case that'll show up from time to time. So that's what the hint down below was trying to get at, was how you can manipulate the function and rewrite the limit. So in the end, you can see this then would be equal to 0. Okay, so as far as your assignment goes, make sure you get a lot of practice with these limits. Most of them, when they're dealing with infinity, are limits that are not going to involve any work. The ones that will involve work are when you have to do a little bit of factoring or when you have to multiply by a conjugate. Try not to use a calculator unless it's absolutely necessary, because the vast majority of these have functions where if you need to solve the limit graphically, they're graphs you should be able to just sketch without a calculator. Okay, so next time in class, I will answer any questions that you have on this lesson, and let me know via email or let me know via the class discussion if you have questions as you go through this.